So, hello again. We are in the process of developing point groups, and in the last video we developed proper monoaxial point groups. So, proper monoaxial point groups, this was developed last time in the part 2 of this series, and we found that there were 5 of them: 1, 2, 3, 4 and 6. Now, there are 6 other point groups which are combination of these rotation axes. So, they are also proper because they have proper rotations only, but then the rotations are about more than one axis, because monoaxial here means that there is only one axis of rotation. So, now we will discuss proper, let us say, multi-axial group. So, multi-axial, they will have more than one axis of rotation. Now, there is severe constraint on how more than one rotation axis can be combined in a space. So, constraint on combination of rotation axes in a space. By constraint, I mean that they can be combined in only few limited ways. In fact, there are only 6 other possible ways. Are there to combine these axes, and one possible ways out of these 6 possible ways, one set of possible ways, one possible way of combining more than one rotation axis, is to place a two-fold axis perpendicular to an n-fold axis. So, I give a brief notation. I say n-fold axis perpendicular to a two-fold axis. So, this is always possible for values of n of 2, 3, 4 and 6. So, if you place a two-fold axis perpendicular to another two-fold axis, you generate a point group which is designated as 2, 2, 2. The Hermann-Morgan notation, and it is called D2 in the Schoenflies notation. If you place a two-fold axis perpendicular to a three-fold axis, then you get a point group 3, 2, which is called D3 in the Schoenflies notation. Similarly, if you place a two-fold axis perpendicular to the four-fold axis, then you get 4, 2, 2, Schoenflies notation D4, and two-fold axis perpendicular to 6, 6, 2, 2, Schoenflies notation D6. D of Schoenflies actually stands for dihedral. So, all these 4 groups are known as dihedral point groups. These are Hermann-Morgan notation, and these are Schoenflies notation. So, in this video we will look at these 4 different dihedral point groups. So, let us begin with the simplest, the 2 2 2 or the D2 point group. So, as per our procedure which we have set up, we will first look at the stereogram and then look at the various operations in the group. So, I start with a primitive circle with 2 reference lines and I take a 2-fold axis which I am placing in the center of the primitive, means the 2-fold axis is vertical, and since I need a 2-fold axis perpendicular to this 2-fold, I place a horizontal 2-fold which will come on the primitive. So, I have drawn this other 2-fold. So, let us start with the equivalent positions. I start with a general equivalent position. See, one reason for calling these general is that I could have taken this point on the symmetry axis itself. If the point is on the symmetry axis itself, then it becomes a special point. So, when we talk of general point, it should not lie on any symmetry axis, or later on when we will consider the mirror planes, on any symmetry plane. So, this is a general point because it is not lying on any of the 2 symmetry axes we have decided. And first I apply this vertical 2-fold. So, the vertical 2-fold will rotate it by 180 degree and will take it there. So, now this is 1 corresponding to the identity and the vertical one has rotated it there. So, this will correspond to 2, but now since I have 2 different 2-folds, I need to designate about which axis I am rotating by this 2-fold. So, the vertical 2-fold, let me call it 0 0 1. So, I give it a designation 2 0 0 1. But there is other 2-fold also. How will this horizontal 2-fold work on this? So, horizontal 2-fold will rotate it by 180 degree, but if the point the initial starting point, general point is above the equatorial plane, a horizontal 2-fold will take it below the equatorial plane, and following our convention, points below we draw by open circle. So, it goes there. Let me show this in 3D. So, let me draw this equatorial plane which is represented by the primitive circle in the stereogram, and I have a vertical 2-fold which is represented by the central 2-fold in the stereogram, and I have a horizontal 2-fold lying in the plane which is represented by the 2-fold on the equatorial plane. And what I was showing is that if there is a point above the equatorial plane like that, if I rotate it about this horizontal 2-fold, if I rotate it about the vertical 2-fold, it will go there. So, it will remain above the equatorial plane after the 2-fold rotation. So, that was what I labeled as 2 0 0 1, this I labeled as 1. But if you apply the horizontal 2-fold on this, you can see that the 180 degree rotation will take it below the axis and will go there. In the stereographic projection, it will come somewhere there on the other side of the 2-fold axis. So, that is where I drew this one, and since it is a result of 2-fold rotation, about the horizontal axis. Let me call this the x axis. So, I call this 2 1 0 0. But then I have to also apply twofold horizontal twofold on the other point which has generated, because the group has to be completed. So, the twofold axis, the horizontal twofold axis not only will act on the initial point 1, it will also act on the resulting point 2001. So, this will also rotate, will go below the plane. Since we are talking of only pure rotations, handedness of all these points are same. So, I get this point. But the question is, what operation this point results from? So, this is actually, I had already gone from 1 to 2001 and now 2100 is acting on 2001. So, this one is actually product of two operations. I first apply 2001 and then I apply 2100. First I rotate about the vertical twofold axis and then I further rotate about the horizontal twofold axis. So, how is this related to the initial? Is there a single operation which is equivalent to the product of these twofold? So, if you see, if I relate one to this final position, these two can be related by another horizontal twofold which is at 90 degree to the initial twofold. So, which means that this new point which I have generated, the product of these two are equivalent to a twofold about the y axis, that is 2010. And you can see that the other 2 points are also related by 180 degree rotation about the twofold along the y axis. So, now my group is complete. So, you can see that there are 4 general positions. So, I can write my 2 to 2 group with 4 operations: the identity, twofold rotation about 10, twofold rotation about 010 and twofold rotation about 001. So, the 3 twofolds and an identity, 4 operations are there in this group. So, the order of the group is 4. So, we said that the product of these 2 twofolds, the vertical twofold 001 and the horizontal twofold 100 gives us a new twofold which is perpendicular to both of these, which is the 010. I have forgotten to mark this point also, I can mark as the twofold. So, there are 2 on the primitive, the 2 ends are marked as twofold, but actually since this is a horizontal twofold, it represents only one twofold. So, this pair of the twofold symbols, this and this for example, is representing one twofold axis, and this and this is representing another twofold axis, whereas the vertical one is represented by just one lens, and that is a single twofold axis. So, let us verify, we will verify this claim. I just made it as a claim and we saw it from diagrammatically from this stereogram, but can we verify this fact by algebraic manipulation? So, we have developed the matrix methods in the previous videos. So, let us try to do that. So, essentially what we are saying that if I continue with my this diagram, call this x axis, call this y axis and call this z axis. So, we can write the matrices for these two-fold rotations. So, this is 1 0 0, this is 0 1 0 and this is 0 0 1. So, let us now develop the matrices for these various rotations. So, first we will develop the matrix for 2 0 1, 180 degree rotation about the y axis. So, recall the way we developed for method we developed for writing the symmetry matrices. So, we just look at the effect of rotation on the basis vectors themselves. So, I have 1 0 0, 0 1 0 lying in the xy plane and 0 0 1 the z axis in this projection is coming out of the plane, I write it in the center. So, if you rotate by 180 degree about 0 0 1, so where does 1 0 0 goes? That will be the first column of your rotation matrix. So, the first column of the rotation matrix is nothing but where 1 0 0 goes after rotation. So, if I rotate about the vertical 0 0 1 by 180 degree rotation, where will my 1 0 0 go? So, you can see that it goes into the negative x axis. So, I write this as bar 1 0 0. Similarly, where the second column of the matrix is where 0 1 0 is taken by 180 degree rotation, and you can see that 0 1 0 also will be taken to the opposite of y axis direction. So, the negative y axis direction. So, that becomes 0 1 0, and finally, the third column is where 0 0 1 goes after rotation, but since 0 0 1 is along the rotation axis itself, it goes nowhere, it remains invariant. So, the third column is 0 0 1. So, this constructs our two-fold rotation axis, two-fold rotation matrix about the z axis. The other one we took was the x axis. So, let us write this. So, now you can quickly see if you rotate about the x axis, then the x axis will remain invariant, the y axis will become negative of itself and the z axis will also become negative of itself. And finally, let me write for 0 1 0 also. Now, this is a rotation about y axis. So, x axis goes to its negative, y axis remains invariant and z axis goes to its negative. So, now let us try to see what is the resultant of 2 0 0 1 two-fold rotation about the z axis followed by 2 1 0 0 two-fold rotation about x axis. So, we have the matrices, we can write that 2 1 0 1 1 0 matrix is 1 0 0 0 bar 1 0 0 0 bar 1 and 2 0 1 matrix is 1 bar 0 0 1 bar 0 0 0 1. Now, you can multiply these two matrices this by matrix multiplication rule, and it is very simple because all the numbers are either 1 or 0. So, the first column, first row with the first column gives me 1 bar here, and similarly if you see it will give 0 here, then 0, 1, 0 and 0, 0, bar 1. But go back, see this matrix here, bar 1, 0, 0, 0, 1, 0 and 0, 0, bar 1, that is exactly that same matrix. So, this is the matrix which is 2, 0, 1, 0. So, we have by matrix multiplication also we see, even if we were not having the stereogram, we by matrix multiplication we can verify that the product of 001 and two-fold rotation about 001 and two-fold rotation about 100 is another two-fold rotation about 010. So, see, matrix multiplication is good and nice to verify such results, and in complicated cases it may be quite essential, but here what we are able to get, and this is the power of a stereogram. So, the effect of matrix multiplication is visible diagrammatically in the stereogram itself. So, this point we saw is resultant of 180-degree rotation about the z axis followed by 180-degree rotation about the y axis. So, this particular point is indeed the resultant of these two, and we also see that we can get to that point directly by a two-fold rotation about this axis, the y axis. So, the resultant of these two two-folds is the third two-fold. So, this completes the dihedral group 2 to 2. Let us continue our discussion now, and let us construct the dihedral group 3 2. In the Schoenflies notation D3. So, now again we will do it stereographically. We start with our primitive circle. Since three-fold rotation is involved, I need reference lines at 60 degrees. So, I draw these reference lines. I start with an general point there, which is corresponding to the identity operation. I place a three-fold in the center. So, my three-fold axis is the vertical axis, and I generate two more points by 120-degree rotation to complete this three-fold axis. So, this, as you have seen when we were discussing the monoaxial group, this corresponds to anti-clockwise rotation or positive rotation about three-fold axis. We designate it as 3 plus, and this corresponds to clockwise or negative rotation about the three-fold axis. So, we call it 3 minus. To make the dihedral group, I introduce a two-fold axis, a horizontal two-fold axis which is perpendicular to the three-fold. So, I place it there. Now, this two-fold will rotate this general position and take it below the equatorial plane there. Similarly, it will work on this point also, point corresponding to the 3 plus, will take it on the other side and below the equatorial plane. and it will act on this and will bring it here and place it below the equatorial plane. So, now I have generated all the points by which result by this threefold and a twofold, and the group is complete. However, if you notice, by symmetry also we expect that if threefold axis is there, then it should act on the other symmetry axis also. So, it should rotate this symmetry axis by 120 degree, and we should expect another twofold axis. Sorry about that, let me get it back. Yeah, we have another twofold axis 120 degree away, 120 degree away. This is my expectation from the vertical twofold, that the vertical twofold should rotate the horizontal twofold by 120 degree, and it should again rotate this resulting twofold by 120 degree. So, I expect another twofold there also. If I further rotate by 120 degree, I come back to the original twofold. So, I do not generate any more new axes now. So, really, although I start with only one twofold, I added only one twofold, two more twofolds, making a total of three twofolds are required to maintain the threefold symmetry. And if you now see with respect to the general position, this indeed is true, because if you now look at, for example, this twofold. So, this will rotate this point from below the equatorial plane to above the equatorial plane by 180 degree and will take it there. Similarly, it will rotate this point by 180 degree from above and bring it below, and these points. So, all these points which are there, all the 6 points which are there are related by this 120 degree rotation about this axis. Similarly, you can see that they are also related by this axis. So, you can relate these 2 points, you can relate these 2 points, and you can relate these 2 points. And you can again verify that. So, we have verified for all. For the first one we had already verified. So, you can see that the points which we have generated are consistent with 3 twofold axes perpendicular to the vertical threefold axis. So, this is my dihedral group 3 2. So, let me write the operations now. If I have to write the operations, so operations of 3 2, identity, then 3 plus and 3 minus, these 3 were there. Other 3 points, equivalent points, should give us 3 more operations. So, what are they? So, this particular point is resulting from the original point by a twofold rotation about this axis. Let us call this the x axis. So, this is 2 1 0 0. Now, with respect to the threefold axis, we select x and y axes at 120 degree. So, if this is x axis, we will have y axis there. Now, let us relate the new points which we have generated. So, this is 2 1 0. What about this point? What about this point now? So, we have already seen that that point can be related to the original point by a rotation about this two-fold axis, and this two-fold axis we will call, now this is between x and y. So, this is a 1 1 1 O direction. So, this two-fold will be called 1 1 O two-fold. So, this point, resulting point is 2 1 1 O. And similarly, this point will come from rotation about this axis, which is my y axis. So, that is O 1 O. So, this is 2 O 1 O. So, now I have the three operations, three further operations, which are just the two-fold axes, two-fold rotations about the x axis, the y axis, and the axis between x and y, which I can call 2 1 0. So, there are 6 operations. The order of the group is 6. Again, these can be verified by matrix multiplications, but we will not do that exercise, but you can try and do it to convince yourself. One point should be noticed, and that is that here we have only 1 2. When we wrote 3 2, we wrote only 1 2. Then why in the designation for this dihedral group we used 3 2's. So, that is an interesting point. Now, notice that I began with an initial two-fold which was vertical, and then I added a horizontal two-fold which was along x axis. Now, the vertical, how does vertical two-fold act on this horizontal two-fold? By 180 degree rotation. So, if you rotate this two-fold about 1 0 0 by 180 degree, this axis goes into itself. So, by the action of the vertical two-fold on the horizontal two-fold, I do not expect another two-fold at 90 degree to it, because the two-fold can rotate the axis only by 180 degree. So, this two-fold, the third two-fold, was in a sense a surprise two-fold, because two-fold rotations rotate the axis by 180 degree and not by 90 degree. So, an immediate expectation that there will be a two-fold axis at 90 degree was not there. So, to express this surprise two-fold, we add a third 2 in this notation. But when you look at the three-fold case, by three-fold we expected the two-fold to be rotated by 120 degree, and when we rotated by 120 degree, I got the second two-fold, and another rotation by 120 degree gave me the third two-fold. So, no new surprise two-folds were there, although 2 new two-folds were there and we have total of 3 two-folds, but I expect the other two-folds where they should be by 120 degree rotation from my original two-fold. So, that is why in the crystallographic notation we have decided to put only 1 2 here in the case of 3 2. So, let us continue with 4 2. So, 4 2 2. So, you again expect a surprise twofold here, that is why the notation is 4 2 2. This is D4 in the Schoenflies notation. Start with our stereogram, have two reference axes at 90 degree. So, I have a vertical fourfold now. This is a vertical fourfold, and this fourfold generates 4 equivalent positions, which corresponds to 4 operations of the group 1, 4 plus, 2 and 4 minus, and then additionally we put a twofold which is horizontal. As soon as I put that additional twofold, I start generating new positions. So, this point is rotated below the plane there. This point will also be rotated below the plane there. This point will rotate below the point there. So, now I have rotated the 4 points about the horizontal twofold to give me 4 additional points below the equatorial plane, giving me a total of 8 equivalent general positions. Now, no more new points will generate by having these two axes. However, new axes have automatically emerged out of this operation. So, you can see that this is also a twofold. So, if my initial twofold was along 1 0 0, so along 0 1 0 also I have twofold, and since fourfold rotates everything by 90 degree, this twofold was not a surprise twofold, because I expected that by a 90 degree rotation I should have another twofold there. However, if you now look at the 45 degree line, the bisector of these two twofolds at 90 degree, they also emerge as twofold, because you can see that these 2 points can be rotated to each other by 180 degree rotation about this new twofold. So, this is again a surprise twofold, because we did not expect a twofold to appear at 45 degree rotation, because fourfold rotates by 90 degree, but here I am now getting, because of that fourfold, another twofold axis at 45 degree. So, to express that surprise, we put the additional 2 there, unlike in 3 2 where we had only 1 2, and of course, in the 45 degree other direction also you have the twofold. So, you can write now the symmetry operations easily. So, if I write 4 2 2, there are, you can see there are 8 equivalent positions. So, there should be 8 operations, 4 operations are with respect to the fourfold. So, that is 4 plus, we have already written 4 plus 2 and 4 minus, 4 plus 2 and 4 minus, and then there is 2 operation of twofold rotation about 1 0 0 also, a twofold rotation about 0 1 0, twofold rotation about 45 degree along 1 1 0, and twofold rotation about 45 degree other way, which direction we can call it 1 bar 1 0, and this one is 1 1 0. So 1 bar 1 0. So 8 operations, it is a group of order 8. If you wish, you can label the points also. So this point is resultant of 2 1 0 0. This point is 2 1 1 0. This point is 2 0 1 0, and this point is 2 1 bar 1 0. So that is the 4 2 2 group. Now you are well familiar with this scheme. So you can develop 6 2 2 quickly. So let us do that also for sake of completeness. So 6 2 2. Here also you should expect a surprise twofold. D6 in so and flies notation. We again start with our primitive circle. Again, since 6-fold rotation is involved, I take my reference axis at 60 degrees and a 6-fold axis in the center. There is the symbol for 6-fold axis. I get 6 points by 60 degree rotations about that axis. The notation for these will be 1, 6 plus, 3 plus, 2, 3 minus, and 6 minus, as we have seen when we were developing the monoaxial point groups. So we can start writing our group. 6 2 2 has these 6 operations, 1, 6 plus, 3 plus, 3 minus, sorry, first let me write the 2, 2 minus and 6 minus, corresponding to the 6-fold axis. But now I add a 2-fold, horizontal 2-fold to make my dihedral group, and as you are now familiar, this will start taking these points below the equatorial plane. This point will come here, point will go there, come here. So equivalent positions are now generated by combination of the 6-fold and a perpendicular 2-fold. But now you can see, and you are expecting also, because 6-fold rotates things by 60 degree, you expected the 2-fold axes, horizontal 2-fold axes, to be rotated by 60 degree. So you get 3 2-fold axes, 3 new 2-fold axes by this process. We can label these 3-fold axes by calling this axis as the 1 0 0 and this axis as 0 1 0. And then becomes 1 1 0. This is negative of 0 1 0 itself, so we don't label that. So these are the only 3, others are just the negative ends of these. So we write these new operations, we add these new operations to our list. So that is 2 1 0 0, 2 0 1 0 and to 1 1 0. So, up to this was expected, but again you have developed unexpected two folds between 1 0 0 and 1 1 0. You have another two fold there. I am using different color to emphasize this. So, this is also a two fold, because you can see that this relates this pair of points and this pair of points, and similarly other pairs. I do not want to clutter my diagram by drawing more lines, but you can verify. So, there is a two fold, although there are only these 12 points, but a new two fold is there which is relating these same 12 points, and correspondingly there will be a new two fold here and here. This is the opposite end of the first one which I drew, and yet another new two fold there with its opposite end here. So, three new two folds have been generated, and what will be these directions? So, let us work out. So, this was 1 0 0, this was 0 1 0, and this one was 1 1 0, and this is a bisector. This one is a bisector of these two directions. So, this new direction is coming in this direction. You can see this is a vectorially the sum of this and this. So, I simply have to add these two. If I add these two, I get 2 1 0. So, this direction is nothing but 2 1 0. Similarly, this direction is nothing but 1 2 0, and this direction interestingly is, you can see that if I write this vector which is opposite of the other end, which is 0 1 0 bar 1 0. So, this will now be a sum of 1 0 0 and 0 bar 1 0. So, it will be 1 bar 1 0. So, now I have found the label for these three new two folds, the surprise two folds, as 2 2 1 0, 2 1 2 0 and 2 0 bar 1 0. This completes my 12 operations of the group. So, 12 equivalent positions and 12 operations in the group. This is the largest dihedral group 622 in our crystallographic point groups. So, in the next video we will develop other multi-axial point groups. So, we have combined a rotation axis with two fold axes, but is it possible to combine more than one n-fold axis other than with two fold axes? This possibility, it will be seen that there are only two possibilities which belong to the cubic point groups. So, this will be discussed in the next part. Thank you now for your attention. Thank you very much.